Hello again. This is Math 2 115 coming to you from the College of DuPage. And the title of this lecture is Application of Prior Theory, the Proof and Counting Things That We Did, to Algorithms. And I encourage you to be an active learner as you watch this video. What does it mean for a computer program to be correct? Well, there's several aspects to this, but it's a combination of things. First of all, you must make sure that it works correctly. You don't type IK instead of IF or use a restricted keyword. The syntax is correct, but when the syntax errors have been removed, the program may still contain certain logical errors that prevent it from producing the correct output. So frequently programs are tested using sets of sample data for which the correct output is known in advance, and often the sample data are deliberately chosen to test the correctness of the program under certain extreme conditions. But for most programs, the number of possible sets of input data are either infinite or unmanageably large, and so no amount of program testing can give perfect confidence that the program will be correct for all sets of legal input data. And not only do you want it to be correct, but if there's an error, you would like to tell the user what the error is rather than just crash the system. So for the past 53 years, with the publication of a paper by this fellow, they have developed methods for proving programs correct at the time they are composed. And Dijkstra, who we'll talk about later, was one of the pioneers in this effort, and he is quoted as saying, "We now take the position that it's not only the programmer's task to produce a correct program, but also be able to demonstrate its correctness in a convincing manner." David Grice said, "A program and its proof should be developed hand in hand, with the proof usually leading the way." In this section, we talk a little bit at a very high level about the format of correctness proofs and the details of one crucial technique called the loop invariant procedure. And we switch from using the term program to using the more general term algorithm. All right, so consider an algorithm that is designed to produce a certain final state from an initial state. Both the initial and final states can be expressed as predicates, logical predicates, involving the input and output variables. Often the predicate describes the initial state is called the precondition for the algebra, and the predicate describing the final state is called the postcondition for the algorithm. Okay, so here are some examples of preconditions and postconditions. An algorithm to compute a product of non-negative integers, the inputs would be variables m and n, which were non-negative integers, and the output would be a variable p equaling m times n. If we're doing an algorithm to find the quotient and remainder of a division by one positive integer by another, the input would be the variables a and b are positive integers, and the output would be q and r, the quotient and the remainder, such that a is equal to b times q plus r. That's the way division works. And suppose, as a third example, the algorithm was to sort a one-dimensional array of numbers. Well, the precondition would be the input variables, all of these numbers in this array, a one-dimensional array of numbers, but the output variable would be b1, b2, b3 through bn, a different one-dimensional array of real numbers with the same elements as the first array, but with the property that they are in increasing order. Now, a proof of an algorithm's correctness consists of showing that if the precondition for the algorithm is true, then, and if the statements of the algorithm are executed, then the post is also true. So you see it's if this and this, then this. It's logic. And often you break it into pieces because the algorithm will be very long, and so you test it in pieces. So you have an assertion 1, which is the precondition for the algorithm. You have algorithm statements, and then you have an assertion 2. Now this assertion 2 is a precondition for going forward, but it's a postcondition for the first part. So you see you can slice this into pieces. And so successive pairs of assertions are then treated as pre- and post conditions for the algorithm statements between them. Now, once all these individual proofs have been completed, one knows that assertion K is true, and since assertion 1 is the same as the precondition for the algorithm, and assertion K is the same as the postcondition for the algorithm, you can conclude that the entire algorithm is correct with respect to its pre- and post-conditions. So you can slice it into pieces to do testing. Now we're going to talk a little bit about one important component of doing this. It's called a loop invariant. The method of loop invariants is used to prove the correctness of a loop with respect to pre- and post-conditions. It is based on the principle of math induction, which we have studied. So suppose that an algorithm contains a while loop, and the entry in this loop is restricted by a condition G called a guard. Suppose also that the assertions describing the current states of the algorithm variables have been placed immediately preceding and following the loop. The assertion is just preceding the loop is called the preconditions for the loop, and the one that follows is the postconditions for the loop. And so the annotated loop will have this appearance. You have the preconditions, you have the while, condition G, statements in the algorithm, and none of these can branch outside of the loop, and end while, and then you have the post condition. So a loop is defined to be as correct with respect to its pre and post conditions if, and only if, whenever the algorithm variables satisfy the precondition for the loop, and the loop terminates after a finite number of steps, and the algorithm satisfies the post condition for the loop, then it is correct. Now, establishing the correctness of a loop uses a concept called the loop invariant. And a loop invariant is a predicate with a domain, a set of integers, which satisfies the following condition. For each iteration of the loop, if the predicate is true before the iteration, then it is true after the iteration. Furthermore, if the predicate satisfies the following two additional constraints, the loop will be correct with respect to its pre- and post conditions. The predicate is true before the first iteration of the loop, and if the loop terminates after a finite number of iterations, the truth of the loop invariant ensures the truth of the post condition. And there's a theorem that states this called the loop invariant theorem, and here was the person who proved this theorem in 1969. So here's the loop invariant theorem. Let a while loop with guard G be given, together with pre- and post conditions that are predicates of the algorithm variables. Also let a predicate I of n, that's the invariant, I of n, called the loop invariant, be given. If the following four conditions are true, then the loop is correct with respect to its pre- and post conditions. There's a basis property, an inductive property, an eventual falsity of the guard, and correctness of the post position. These are the four steps. So the basis property is the precondition for the loop implies that I of 0 is true before the first iteration of the loop. And then, this is really anchored in the property of math induction. If for every integer k, if the guard and the loop invariant ik are both true before an iteration of the loop, then I of k plus 1 is true. So you see, when you're proving this, you're often using induction. Eventually, you get out of the loop, and that means that the guard eventually becomes false, so you can exit the loop. It is not an infinite do loop, which does no one any good. And the last part of this theorem is the correctness of the post condition. And so once you get out of the loop, that means that the guard condition G is false and I of n is true, then the algorithm variables will be as specified in the post condition of the loop. This follows very easily from the principle of math induction, because if this is the predicate that satisfies properties 1 through 4 of the invariant theorem, then properties 1 and 2 are the basis and induction steps needed to prove that if the while loop iterates n times, then I of n is true. Thus, by the principle of math induction, both Roman 1 and Roman 2 are true, and so this statement is also true. Property 3 says that the guard eventually becomes false, and that means usually you reach a number that says that you can exit the guard. So you've iterated a finite number of times, say n. And often this is by the well-ordering principle that you can conclude that there is a smallest one, that eventually this will happen. And so since statement 4 is true by assumption, its hypothesis is true by the argument just given, it follows by modus ponens. You see, we're going back to those fundamental principles. This conclusion must also be true. That is, the values of all algorithm variables after the execution of the loop are as specified in the preconditions, in the post condition for the loop. Now, this is pretty deep business, and developing a good loop invariant is a tricky process, and learning how to do this is well beyond the scope of this course, but it is very worth pursuing in more advanced computer science courses. Another tricky aspect arises from the fact that execution of an algorithm is a dynamic process that takes place in time. As the execution progresses, the values of the variables keep changing, yet often their names remain the same. So just in this discussion, we're going to make a distinction between the values of a variable just before you execute an algorithm statement and just after, and we'll call the subscripts old and new to the variable name. Examples are always worth 1,000 words, so we're going to, at a high level, do this, and there's a lot of detail here about how to do this. So suppose you have you're running a loop to compute a product. So the input is going to be a real number, x, and we're going to take x times n. So the way we do this is we will start having a do loop, and we'll start at I equals 0, and the product is equal to 0. But then we'll start going, and we'll say the product is equal to the product plus x. So we're adding x to itself each time. And you know multiplication is repeated addition. 5x is the same thing as adding x to itself 5 times. And then we increment. I is equal to I plus 1. So then we go back. Now I is 2. And then we add it again. And then we increment. I is 3. And eventually we will end, because we will end whenever I is not when I is equal to m. And so the loop invariant here is I of n is I is equal to n, and it's a dual condition. The product is nx. And the guard condition is you continue this loop until I does not equal m. So we use the loop invariant theorem to prove that the while loop is correct. So this is the guard condition, and when this is false, that means I equals m, then you'll exit the loop. Okay, so the basis property, we have to say, oh, is I of 0 true? Well, if I equals 0, the product is 0, so that's true. And then we say, suppose that I does not equal m, so we're still going, and I of k is true. Then you have to show that, gee, if I add one more, that makes this k plus 1 times x. And of course it does. Here's a little bit of a proof of that. We have to say, oh, does the process ensure that eventually the guard is false? Well, we're making I equal I plus 1 each time, so eventually it will get big enough such that I is equal to m. The guard is false and we can exit. And then do we get the correct answer? And if you trace through this, you'll find that you do get the correct answer. And so the correctness of the, we do have the correctness of the post condition. Now here's another one that's even more involved mathematically, but this is the correction of the division algorithm. Okay, so what we're really trying to do is we're giving two numbers, a and d, and what we're trying to do is we're trying to find numbers such that a is equal to qd plus r. That's basically, we're dividing a by d, and we get a quotient and a remainder, and the remainder has to be between 0 and d. Okay, and so here's the loop that we have. We have a precondition. So while r is less than or equal to, or greater than or equal to d, you see we stop whenever the remainder is less than d. Well, in the same way that multiplication was repeated addition, division is repeated subtraction. So we subtract d, and we take the new r, and then we also increment the quotient by 1 because we subtracted it, and we go through here. We count the number of times that we can, subtract d until r is strictly less than d. That's the guard condition, and then we can exit. And we should then know what is the quotient, q, and what is the remainder, r. And we have those when we exit the problem. Now we have to prove the correction of this, and here's the loop variant. So I of n is equal to the remainder, and that is a minus nd. That's bigger than or equal to 0, and this is the and condition, and n equals q. And the guard is, we work until the remainder is less than the divisor. So we check to see, is I of 0 true? I'm not going to take you through all this, but I of 0 is true. We have to show that if we're still within the guard condition and I of k is true, then ik plus 1 is true after the loop. And it is. Quite a bit of calculation to prove that, but it is, and I'm trying to show you the structure. Hence, I of k plus 1 is true. Eventually, the guard is false because we're incrementing that. And again, often the argument is that the well-ordering principle that we talked about back in an earlier chapter, I think it was chapter 3. And we have to check to see, is there correctness of the post condition? And we do find that as well. So you see, there are proofs, and substantial proofs involved in the computer programming. And here's an example of the correctness of the Euclidean algorithm, which is finding the greatest common divisor of two numbers. And again, what you see is we start with a basis property. And in fact, we have to define what is I of n. I of n in this case is the GCD of AB is the same as the GCB of capital A, capital B. And the guard is that B does not equal 0, because when B equals 0, you terminate and you exit the problem. So we have a basis property, and we see that I0 is true. We say if we're still in the while in the do loop, and if I of k is true before the loop, we have to show that I of k plus 1 is true after the loop. And we show that. Now that's actually quite a bit to show, but this is what we need to show, and at the end we do show that assuming I of k, we get I of k plus 1. That's the induction that we proved earlier and talked about earlier. Here again, we realize that G, the minimum has to be 0, so that it does hit 0. The guard is false immediately following the case where that is calculated, and so eventually the guard is false. You get out of the loop, and then you have to check to see if the post condition is correct, and it is, as was to be shown. Again, quite a bit of work. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. More about algorithms later. May God bless you all.